Yay, how is everyone? Happy Friday. Happy end of week 4. We're coming up to the halfway point of the course, which is just crazy. Because it feels like we just started. Alright, so hopefully you turned in PA2 and it was downloadable and all of that good sort of stuff, and if not, then I will try again tomorrow morning at 8. It's a 20-point deduction, but it's still better than a 100-point deduction, so if you haven't turned it in or corrected the problem, please do that before tomorrow morning at 8, and I'll make a second download attempt then. Otherwise, I will get these graded over the next few days and hopefully have them graded by Monday so we can talk about them in class next week. But even more hopefully, I'm anticipating people were very successful with this assignment and that everything will work perfectly and we'll all get hundreds, which would be great. Alright, so any questions, lingering questions, ODPs, things like that. We'll take a break from ODPs for the weekend. We'll come back to them on Monday and start doing some ODPs related to stacks and queues and or hashes. Alright, well let's just eyeball. I didn't give you an ODP, did I? Because it would have been silly. All right. Well, let's do a little more with stacks and queues. So I want to look at one more sample application for stacks and queues, which is mazes, not maxes, but maze running. So you know, you got a maze and you're trying to find a way through it. The solution is always, you know, start at the end, work your way backwards, because most people who make mazes, they design them from the start. But if you begin at the finish, there's usually, you know, fewer choices. But if you don't know that, if you're not cheating, right, how do we solve a maze? There's two fundamentally different approaches, and we're going to see these two approaches come up multiple times in the rest of this course. The two concepts here will be, here's the buzzwords, depth first or breadth first. We're going to help Mr. Panda find his way home, so we'll get back to that. So imagine you have some space that you're trying to explore, right? There's two sort of fundamental ways to do this. One is to and you know, imagine there's a bunch of points here that you want to visit. One is to start, you know, here and go down as far as you can, and then come back up and go down again and come back up and go down again, and basically try to spend as much of your time as far down as possible. And then when you've explored all of these spots, you come back up one level, and now you come down and you explore all of these. And then you come back and you explore all of these. And so the primary direction of travel is deeper. This is very abstract. There's a different approach, which would be to go across first. So same idea, you've got some space you're trying to explore, and we begin by moving over as far as we can. And then when we can't move over any further, we back up one spot and we move over again. And we travel like this. And then we come back up and so on. Okay, this is going to be a lot less abstract when we talk about binary trees or trees in general. Um, but we can see this pair of concepts in, trying to help Mr. Panda find his way home. So here's how most people solve mazes. We start off here, and let's say we're going to use a search order, which is right, straight, left. So anytime we come to a decision point where we could go more than one way, we're going to try going right first. If that doesn't work, we'll try going straight. If that doesn't work, we'll try going left. All right, so we start here, and there's no choice. We have to come down here. We come here and we've got a choice. Should we go straight or should we go left? Well, here's our first decision point. Let me call it A. And at A, we're going to choose, we can't go right, so we're going to choose to go straight. And we come over here, we come over here. Here's another decision point. We could go straight or left. So we'll call that decision point B, and we'll say, let's go straight. And we go further, we go further. We come here, we've got another decision point. We could go straight or we could go to the right. So we're going to go to the right. Now you and I, right, we wouldn't do that because we can see it's a dead end, but a computer doesn't have that look ahead unless we teach it how to look ahead, which basically means, go to the right and see what happens. So we're just following this algorithm. Anytime that there's a choice in which way to go, first we're going to try going right, then straight, then left. Okay, so we're going to go right, and I'm going to keep track of my decision points over here. So A, I went straight, B, I went straight, C, I went to the right. And now I come down here, and I've got to go here, I've got to go here, I've got to go here, and there's a dead end. So I made a wrong turn somewhere. It's a little bit like Dijkstra's algorithm. It's not as fancy as Dijkstra. I made a wrong turn somewhere. I don't know where. Could have been any of these places that I made a branch point. Usually what humans do is we go back to that last place where we made a decision, which in this case is C, and we say, okay, instead of going right, let's try going straight. So we'll come back here and we'll try to go straight. And we'll come here, and here's another branch point D. And we could go left or right. Well, we're going to try going right first. And we come down, and here's another branch point E, and we can go straight or right. And I'm looking from the point of view that we're moving in, so right is like that. So we're going to go that way. All right. Now we're going to start getting a little deeper. So here's the decision point F. And we could go right, or we could go straight. So we're going to try going right first. And that dead ends us. All right, we go back to the last decision that we made, which is F. And we say, okay, right didn't work. Let's try going straight. So we go straight, and we've got to come down here, and we come down, and there's a dead end. So we hit another dead end, so we come back to our last decision point, F, and we say, well, we tried to go right, that didn't work. We tried to go straight, that didn't work. We can't go left. The problem is not here. The problem came before this. So we remove F, and we back up to the last point before that, which is E. And we say, okay, we tried going right, that didn't work. Let's try going straight. And so now we're going to go down this way. If you continue doing this, you will eventually solve the maze. But what happens when we do this as humans, right? We sort of, usually we take our finger and here's the part where we're not sure where to go. So we put our finger there and we keep going, and maybe it's a mental finger, right? When we come down here and it doesn't get us anywhere, we know that this was the last point we made a decision, so we continue down this way. And that's pretty unambiguous. And so here maybe, I don't know, should I go that way or this way? Well, I'll try going this way. No, 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 no. Nope, none of that works. So I come back here and I go a different way. And hey, there's Mr. Panda's home. That's a strange looking home. It looks like a search icon from a web page. Alright, yeah, we should make a maze solver for PA3. That would be fun. So the way we're doing this, does this feel like a stack or a queue? If you had to pick one or the other. Definitely a stack. It feels stack-based because when we have to go back to a prior decision, we're going back to the last decision that we made. Right? So it's a LIFO. The last decision we made is the first decision that we're going to reevaluate. So it's got that LIFO structure to it. But we don't have to use a stack to solve a maze. We can do this with a queue. It feels kind of awkward, at least to me. But let's try this with a queue-based approach. So we're going to start here. We're going to come to a decision point A. Let me put it over here. And we'll stick to the right, straight, left option. So we can't go to the right, we'll try going straight. We come to another decision point, that's B, and we can't go to the right, so we'll try going straight. And we go a little further, and here's another decision point, C, and we're going to try going to the right. And we go to the right, and we come along, we come to a dead end. So something is wrong. We have to change one of our decisions. We could go back and reevaluate this first decision that we made. We could say, okay, let's go back, and instead of going straight from A, let's go to the left. And so we remove this from the head of the queue. And we say, okay, let's go to the left. And we put that in the back of our queue. And going to the left does not help us. So now we go back to the head of the queue, which was where we went straight from B, and we remove that, and we say, okay, let's go left from B. And we try that, and that doesn't help us. And so we say, okay, well, let's go to the head of the queue. And we went right from C, let's try going straight from C. And that gets us a little further. And then here's D, and we'll try going right. And we'll come down here, and so on. We're still going to explore all the possible options, but we're doing it in a different order. And which order is correct? It kind of depends what your criteria is. It depends what your problem is that you're trying to solve. Okay, this is a breadth-first approach. And we can describe the process of solving a maze with a tree. This would be a three-way tree where at each point we have three possible ways that we can turn. And it's a question of how are we going through the set of possibilities. Are we going across or are we going deeper? And yeah, so someone said it seems like a lot more work. It's KVL, KCL, right? Probably 90% of students find KVL a lot easier than KCL, right? Doing the loops just feels better than doing the currents. But about 10%, it's the other way, okay? Most people probably feel more at home doing stack-based exploration of a search space. I think as humans, at least in Western culture, we tend to do things more stack oriented than queue oriented. We're very interrupt driven, right? We respond to things when they come up, and then we go back to what we were doing. It's part of a multitasking culture, but it's not inherently different. It's the same thing in 250. Sum of products are product of sums, right? Most people find sum of products easier than product of sums, but they're really the same thing. And at some level, stack-based and queue-based are really the same thing. It's just, which end do you take things out from after you've put them in a given place. All right, so we'll get Mr. Panda all the way home. There you go. Yeah, someone says they remember not liking POS, and that's why they remember it. And I'm exactly the same way. I find product of sums inherently more complex, but if I really dig into that, it's simply because I have certain biases about ands and ors, and I don't think about them equally. I think of one fundamentally differently. I think of one as more natural. Right, I think of this and this and this. So sum of products just kind of falls out. All right, let me do one other application of a stack. And this is a classic programming problem. I don't think I'm going to assign this, but this is something that you'll probably see in other courses. This is the idea of a stack-based calculator. So how does a calculator work? I mean, when you type, 2 plus 3 times 5 plus 6, right? And your calculator magically does this first and gets 15, plus 2 is 17, plus 6 is 23. How does it do that? How does it see the 2 plus 3, but instead of jumping ahead and saying, let's add these together, it sees the multiplication and does that first? And then if you have parentheses, everything gets really weird, right? So I don't know if anyone here remembers this, but way back in the 70s when calculators were first coming out, you could buy a calculator. It was about $100 for a calculator that would like add, subtract, multiply, and it would kind of divide, but it was integer division. It didn't have decimals. It was just all whole numbers. And scientific calculators started to appear. The coolest calculators were made by Hewlett-Packard. They looked fundamentally different. They were the engineering calculators, but they had a quirk to them. And if someone asked to borrow your HP calculator and they weren't in the cool kids club, they wouldn't know how to use it. Because HP calculators originally, they did not work the way other calculators work. They used something called RPN, reverse Polish notation. And RPN was a different way of describing an operation you wanted performed. Now when you say something like 2 plus 3, you're saying operand, operator, operand. We're saying here's a noun, here's a verb, here's a noun. And do that verb to those two nouns or objects. RPN was different. RPN, you would say operand, and then what you want done, operator. So if I wanted to evaluate this on an HP calculator, I would type the following. I would type 2, and then I would type 3 and 5, and then I'd hit the star key, which said multiply 3 and 5, and then I hit the plus sign, which says add that number I just got to the number I entered before that. So that would do 2 plus 3 times 5. And then I'd do a 6, and I'd say plus, which says add 6 to the thing I've got so far. And that would pop out 23. And that was weird, you know, when we first encountered it. I was in high school at the time, and it was like, hey, this is broken, you know. But it's weird. The more you play with this and the more you use this, the more natural it starts to feel. Until eventually, this is how you kind of think of arithmetic expressions, and the idea of typing 2 plus 3 star 5 plus 6 feels kind of like, you know, well, that's how humans do this. That's not how computers do it, you know. And it turns out this is really kind of what goes on in the brain of a computer. When you have an arithmetic expression, it actually gets translated into something like RPN. And we'll learn how to do that in a couple of weeks when we do trees. And it turns out we can take this expression, we can build a tree, and then by looking at that tree a little sideways, we suddenly get out RPN. But what's cool about RPN is it's really easy to write a program that will evaluate an expression like this. Now, evaluating an expression like this is complex, because you've got to have look ahead, you've got to understand precedence of operations, you've got to be able to do parentheses, and so on and so forth. You don't need parentheses with this, right? If I wanted to do 2 plus 3 times 4 plus 5, in RPN, I could do 2, 3 plus 4, 5 plus times. And it says take 2 and 3, add them, take 4 and 5, add them, and then multiply the last two answers. Embrace the discomfort. So how do we evaluate an expression in this form? We can do it really easily with a stack. So this should give us, you know, 5 times 9 is 45. This should give us 45. This should give us 23. All right, so how do we do this with a stack? Straightforward algorithm. So start with an empty stack. If you see an operand, push that onto the stack. If you see an operator, pop 2 things off the stack, apply the operator, push the result. And just do that in a loop. And then at the end of the input, the answer is at the top of the stack. So there was an enter key, so you would type your number, enter, type your number, enter, type your number, enter, and then hit the operand. So, you know, if I wanted 23 times 5, I would type 23, enter, 5, enter, and then star. But I'm skipping that here. It's a good question. All right, so what does this look like? Let's go ahead and do 2, 3, 5 star plus 6 plus. All right, so there's an operand 2. We'll put it on the stack. There's a 3. There's a. I'll grow the stack upwards. There's a 2. There's a 3. There's a 5. Here's a star, so what do? Pop off the top two numbers, 5 and 3, apply the operator, so multiply them, that's 15, push the result. Hey, here's a plus sign, what do? Pop off the top two numbers, apply the operation, 15 plus 2 is 17, push that onto the stack. Here's a 6, put that on the stack. Here's an operator, pop off the top two entries, 6 and 17, add them together as 23, push that on the stack. We're at the end of the input, our answer is the one thing remaining on the stack. Alright, so let's go through this one. I'll let you figure out the answers this time. So what did we do with the 2? Here's my stack. Push it to the stack. What do we do with the 3? Push it to the 3. What happens at the plus? Pop operator. Okay, I pop off the 3 and the 2. The operator is a plus, so what do I do with the stack? Push a 5. There's a 4. Push the 4. There's a 5. Push the 5. Alright, what's the plus do for us? Pop, pop. Apply the operation. That gives us a 9. Push that on the stack. Good. And then there's a star. What do? Same thing. Pop, pop. Apply the operation. Push that onto the stack. That's the end of the input. There's one thing on the stack. That's our answer. So this is how your compiler converts arithmetic expressions into assembly language and ultimately machine code. Yeah, it is fun. So first you have to take your expression like this and change it into RPN. And then, you know, so if you're doing something like hey, my name's Nick and I want to evaluate the following. So I'm doing my erroneous quadratic formula piece here, right? So in RPN, right, this would be B times 4A, and you can write these multiple ways. I could do 4A times C times and then plus, or I could do 4AC times and then plus, but we'll get the same thing. And so what would it look like in C? Well, if we have push and pop functions, right, we'd push B, we'd push B, we'd push pop times pop. We'd push 4, we'd push A, we'd push pop times pop, we'd push C, we'd push pop times pop, we'd push pop plus pop, and then we'd pop off the final answer. So that's not what ends up in the machine code, but that's effectively what you're doing. But this kind of analysis would let you write assembly language that would do this operation. Yeah, it can kind of clear up stacks. I mean, it's nice to have applications, and this is, you know, sort of the quintessential stack application. Here's a calculator. We might do a calculator program in 223. I've had people do that for GUI projects sometimes. All right. Final questions on stacks or queues. All right, on to hashes. So, hashes are about storing and retrieving information. They are related to password hashes and MD5 authentication and things like that. They're related to theories of cognition and how, you know, our minds are able to process information as well as they do, and in ways that feel fundamentally different from how computers process information, unless we do a great deal of work to make the computer mimic our minds. So I want to start off with kind of a narrow subset of everything that hashes are, and just kind of think about this in terms of search, right? So searching a set of data for some piece of information. So let's suppose we have data collection with a name and a phone number. All right, so let me do an office number. I don't want to write 7-digit numbers all morning. So a name and an office number. So here's Nick, and my office is 115. And here's Izad, and his office is 119. I think these are fake. And Tina is 103. And Carol is 105. And Scott is 111. And imagine we have, you know, a zillion entries in this database. And we want to know, where is Tina's office? Okay, this is sort of the central problem of most of what we're studying in this course. How to manage a chunk of information efficiently. So one option is to store these in an array, right? We could make an array of structures, or we could make parallel arrays. And, you know, we'd have a variable that says you've got 5 zillion of these things. And so we go through each element in the array and we say, you know, does this name match Tina? No. Does this? No. Does this? Yes. Okay, Tina's room is 103. And that's great in this case, but you know, if Tina was the 5 zillionth entry on the list, that would take us 5 zillion operations. So we could sort this, right? We could have a sorted array, and we could play high-low. And we could say, okay, let's look at the middle entry, and you know, Tina's name comes after that, so let's check the last half of the list and cut it into quarters and so on. And that's going to be better. But that can still be expensive. That's a log n operation. And even though log n doesn't seem like that much, the expense of doing the log n operations on a large database, especially if the data is very complex, can be considerable. Right? We could put this in a linked list, and it's kind of like an array. You start at the beginning and you go through, and so on. And when we talk about trees, we'll see how to do this in something like a linked list with order log n complexity. Um, but it would be really nice if we could do this in order 1. If it took a fixed amount of time to pull out information out of this, no matter how big the database was. Okay, this is kind of what our brains do. You learn a bunch of stuff, you have a bunch of memories, you have a lifetime of experiences, but you can still access data very efficiently up to a point. And you know, when you're 20 years old instead of 10 years old and you've had twice as many memories, it's not taking you twice as long to think up, you know, what's this person's name? Or you know, do I put my pants on the top of my body or the bottom of my body, right? I mean, these are memories we have to recall, and we have rapid access to these memories, seemingly independent of how big the collection of information is. And so it's not exactly order 1, but it's pretty dang close. And this shows itself really clearly when, for example, you're walking down the street and you hear a song, or you catch a whiff of a smell, and suddenly you're thinking of something from, you know, 10 years ago that you hadn't thought of in a decade, and boom, it's there, right? And how did that smell get to this piece of data that was like buried way down in the list, right? So the concept here is association. And a hash is an example of an associative memory. So someone suggested have 26 arrays organized by the first letter of the name, and now you have a smaller search problem. And if the names are nicely distributed, right, we'd only have to check this array of names starting with a T to find Tina. And it's possible that, you know, there's an imbalance, and most people's names start with the letter B. And so if you look for one of those, it takes you a really long time, whereas the person whose name starts with a Z, there's only like 5 people there, and that's really quick. But assuming even that it's balanced, right, we could cut down the time by a fixed amount. It's still going to grow with the number of entries, though. But what do we do if we have 26 arrays and we use the first letter? We're using the thing we're searching for to help tell us where to look. And so we have these arrays that we label A, B. And we look at the thing we want, Tina, and it says, oh, search in here. So someone said popular letters, maybe you'd have to go 2 letters to effectively search. So let's do that. Let's make an array AA. Let's make an array AB. Let's make an array AZ. Let's make another array for BA, BZ, all the way down to an array for ZZ. We've got 26 times 26 arrays now. But a really good chance that whatever name you're looking for, there's not too many things in that array. Now, how do I get to one of these arrays? Well, I could put them in a big array. This could be an array of arrays. And so if I take the first letter and multiply by 26, and I add the second letter, right, assuming A is 0 and Z is 25, if I take the first letter, multiply by 26, add the second letter, that will give me an index in my array of arrays. And then I search that array, and, you know, there's the name. Or I search that array and, you know, it's only got 3 entries in it, and I don't find the name. Hey, the name's not in our database. Well, I might have a lot of data that has the same first 2 letters, so maybe I want to use the first 3 letters of the name and make an array of 26 times 26 times 26 arrays. Still 2-dimensional, but a whole lot more of these. So if you know me in the way that I like twisty-turny things, you can probably guess where this is going. If we suppose the longest name has 20 letters, why not make 26 to the 20th arrays and have basically one array for each possible name? And now, you know, if I take the person's name, it's going to map me to exactly one of these 26 to the 20th arrays, and I'll look in there and there's their office number right there in the first spot. And that's order 1, right? You take the number of letters in the name and you multiply by increasing powers of 26, and you add those all together and you get some ridiculously huge index, and you say, oh, this is an array 16 gazillion, and you go to that array in this 2-dimensional array, and it's got 1 entry which is for this person, and there's their office number. That's what a hash is. A hash is basically creating a unique storage spot for every possible name. And so if you want to find somebody's office, you take their name, you run it through a function which says, where is this name stored? And then you go right there and pull out the name. Okay, that's a theoretical hash. We're obviously going to have to do something when we come back to reality. But in theory, that's what we're doing. We're creating one entry spot for every possible name. And so we can go straight to where the name is stored. We don't have to search. We don't have to say, you know, is it here, is it here, is it here? We take the name and we say, oh, I know where that's stored. That's stored right here. And we just go there, we get the information we want. All right, so how do we know where to find that information? It's a mathematical function. There's a thing called a hash function. And so let me just call this function h. So this hash function, we give it a string, which is the name of the person whose office we're looking for, and it gives us back an index, which is an integer. And now if we look at table bracket index, that's where we're going to find the information we want. So it's pure order 1. So where is Izad's office? Well, take the name Izad, I-Z-A-D, run it through this hash function, which, you know, is some quick calculation, and gives us back a number, you know, 17,000,003, and go to element 17,000,003 in our table, and sure enough, at that location, we've got the name Izad, we've got the office number 119. Fixed access time. Now the time is fixed, but the amount of memory you need for this is ridiculous. Right? If your names can be 20 characters long, you need 26 to the 20th entries in your array so that each name can be stored in its own location. And that's not feasible. it's a little more feasible with, like, gray matter. We've got lots of storage space. So this hash function has a second duty. It takes a name and it gives us an index telling us where it's stored, but it also takes into account the fact that we don't have 26 to the 20th possible locations. It allows us to have some redundancy. It may turn out that Izad and Scott both map to the same index. Unlikely, and hopefully not, but it's possible. If we really wanted, 20 character names, and each character could be 26 possible letters, that's 26 to the 20th different names. Alright, so we're not going to have 26 to the 20th locations in our array. So we start doubling up, or tripling up, or quadrupling up. And we let different locations hold potentially more than one name. Yeah, I miss Scott. I used to see him every morning when I'd walk into class. He'd be coming out at 121. He's doing machine learning in spring, though. CS222, he's offering that again, as far as I know. If you have space in your schedule, it's a 2-credit course. Got really good comments from students last year when he taught it, so that could be a fun one to take. All right, so how do we write a hash function that doesn't require this ridiculous amount of space? So here's a sample of a reasonable hash function. Yes, CS222, I believe, is 2 credits. I could be wrong on that. It could be, but yeah, intro to machine learning. So a hash function is going to go from the set of names into some set of indexes. Let's just say we'll go up to index 10. So instead of a zillion entries in our array of arrays, we're going to have 11 entries. So we want to take a name and we want to turn it into a number between 0 and 10. And then that's where we're going to store the office number of that person. So here's a sample hash function. Let's just add up the letters in the name we're looking for. And so we'll just, do a summation from element 0 to the last element, string length name minus 1. We'll add all of those together. And then we'll reduce it modulo 11. So that's going to give us a number from 0 to 10. And so if you want to find a name, we'll run the name through the hash function. We'll get a number from 0 through 10. And we'll say, hey, let's look at that element in the array and try to find the name. And so this is, what we were doing when we were, for example, just looking at the first 2 letters of a name. But it lets us take into account, the entire name, so that 2 names that start with the same letter don't necessarily go to the same location. But this is an approximation of an ideal hash. If we've only got 11 places to store something, we've got 100 names, we're going to have overlaps. We're going to have a lot of cases where there's more than one name stored at the same location. And so that's something called a collision. And we have to deal with collisions. Alright, so we'll start from there on Monday. But that's an intro to the idea of hashing. Alright, I will see you next time. Have a good one.